When you meet someone with a tattoo of the molecule for adrenaline on their neck, I can tell you firsthand, spend some time with them. You're going to be in for an adventure, it's guaranteed. In today's episode, Professor Bryan Fry, he joins me, and what an adventure this one is. Now, how do I describe this episode to you? This one for me was like a kid in a candy shop. Talk about me nerding out on really fascinating science. Now, let me talk to you about something. Have you ever been around something that was venomous? Now, the average person chooses to go in the opposite direction. Bryan is quite the opposite. He's not your average person. That world, well, it's his candy shop, and he goes running towards it. Now, let's talk venom for a second. Did you know that an animal in the same species can be exactly the same, but in different environments, their venom can be completely different? Here's an example. The venom's proteins or neurotoxins can do different things. One could be for blood to coagulate. One could make their blood actually have an anticoagulant and keep flowing so they bleed out. Or one could stun you. Now, this one is my description, by the way. This whole episode could have been just about venom and the crazy things it does. Seriously, we could have talked about this for hours. But we also got to talk about Komodo dragons. Bryan's a leading expert on Komodos, and when you hear about some of the craziest things about these guys, you're going to be blown away. Now, here's some trivia. The very first King Kong movie was loosely based on the Komodos because when they were first discovered, they were on this remote, exotic place. Now, think about it. Think about King Kong. Do you remember? He was found on this remote island. There you go. Now, Bryan's debunked some of the things about the Komodo. He's proven they have a venom, and that was to the chagrin of a lot of people. And we get into this, but that's just the tip of the iceberg. These guys have been measured to be as big as 10 feet long and weigh about 300 pounds. They're highly intelligent, and they're considered an apex predator. Basically, that means they're the top of the chain predator. Basically, what that also means is don't mess with these guys. Now, I could go into so much about the Komodo, venom, and a lot more, but let me just nerd out a little bit more. Bryan was amazing, and this is a monster, of an episode. So I'm going to save everything just so you can listen to Bryan and nerd out on this episode with Bryan 2.
For real, 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 for real. Got a bunch of furry friends and I love them all the same. I'm an animal lover, veterinarian is the name. Let's share some pet stories from heartwarming to strange. Losses and gains, from wacky to insane. For real. You're now tuned in to For Real with your host, Mark Kyle.
Hey, everybody, and welcome back to the For Real podcast. My guest today is Bryan Fry. I could probably go into everything he does, but it would take us the entire time. We wouldn't even be able to do the episode. Bryan, welcome to the show, and I really can't wait to talk to you.
Thank you for having me.
Well, I know you're down in Brisbane now in Australia, and I thought what we would do is let's start from. I know you've told me you moved around a lot, but let's start when you were younger. I've read an article that you've been interested in reptiles since you were really young. So let's kind of go there and move forward, and we'll get into the dragons after that.
It comes down to a couple of formative events early on, as is so often the case. So in mine, it's the first memory that I have is actually being in a hospital bed and actually strapped down, completely restrained, because I had spinal meningitis as a toddler that I picked up from a daycare when my dad was stationed in Washington, D.C. on a military base there. And so they had me in the hospital over in that area, and it was brutal. That my parents were just in the middle of moving. He was being stationed somewhere else. And I came down with this disease that even now still strikes fear into the heart of parents and doctors. Where like there was an outbreak here a few years ago. 16 kids at a summer camp got it, and 6 of them died. So it's, even now spinal meningitis is, absolutely, awful. And it's one of those diseases that you don't get away from unscathed.
Right.
So in that case, when the reason they had me restrained was that in order to deliver the medicine and IVs to me, they had to surgically implant tubes on the inside of both my ankles and actually on my temples as well. So I've got matching scars on the inside of my ankles and on both my temples. And I kept pulling the lines out, like this little hairless monkey. I just wanted out of there. So they had to actually, heavily sedate me and actually strap me down in order to deliver the life-saving medicine. But spinal meningitis is one of those diseases that you don't come out of unscathed. So in my case, I came out of it with permanent deafness in my right ear, and also with pretty dodgy balance. It probably linked obviously to the ear damage, since the middle ear controls so much of our balance.
Right.
So I had this very early experience with these invisible substances. It might as well be magic, where it just puts your life on a completely different trajectory. And of course, at that point in time, kids and mental health wasn't really thought of too much. So it was, I was constantly reminded of the fact that, I had this disease and I survived, but other kids died from it. So I ended up with a, gargantuan case of weapons grade survivor's guilt,
Wow.
which is something very common, for people who have, gone through, disease outbreaks, through to, soldiers who survive in war, but the rest of their, battalion or platoon got wiped out. It's that why me kind of thing, and you kind of, it's a funny paradox where on one hand it ends up, inspiring you. So a lot of my science is driven by trying to alleviate suffering, but it does your head in so much, particularly when you're a kid,
Yeah.
that it also manifests as, incredible self-destructive behavior. So, it's, one of the reasons I've racked up so many broken bones is I've done a lot of really stupid things, along the way. Like, I'm the only person I know who's had to learn how to walk 3 times. I had just learned how to walk when I got spinal meningitis, had to relearn how to walk when I got out of the hospital because my muscles are so wasted. And then I had to learn how to walk again 10 years ago when I broke my back for the first time. I've broken my back on 3 separate occasions.
I was going to say first time.
Yeah, but the first one was the most spectacular. I broke it in 3 different places, and they had to rebuild the vertebra with cobalt metal alloy with artificial discs in between. I was in the hospital for 4 months, and when the X-rays look like Wolverine, it's pretty cool.
Wait. I just want to know. So when you were breaking it, were you doing some kind of crazy acrobatic thing, or was it just falling off a cliff, or what was it?
No, I was on the top of a 4-meter termite mound catching a lizard.
Oh, there we go.
The termite mound broke. One of those gargantuan cathedral termite mounds that you get up in northern Australia.
Yeah.
And had enough free fall time to think this is going to hurt, and landed on another termite mound about 1 meter off the ground, flat on my back, and just obliterated 3 of the vertebrae.
Ooh, I can feel it.
So I had that early formative experience, and then combined with that was that my mother was a daughter of UN diplomats from Norway, so they also grew up bouncing all over the globe. They lived in Africa a couple times, and so she had photo albums of their time in Africa where they had like cobras popping up in their garden. They even had a black mamba in their house one time. They had a gaboon viper pop out on one of their tennis courts. So, I saw these pictures of these amazing animals that also injected the same sort of invisible substances that caused, all that permanent damage from spinal meningitis and, almost took my life. So it seemed like just a natural marriage between those two. So I was like 4 years old when I announced that I was going to make venomous snakes my life's work. And unlike, little Timmy who wanted to be an astronaut, I actually ended up doing it.
Right. I mean, that's rare. It's funny. It's interesting for me to talk to people that kind of knew what they want to do right away. I never know. Matter of fact, I'm not quite sure I know what I want to do yet. So that I'm always impressed by that.
Yeah. And then from there, everywhere we moved, I would always catch the local animals. Ended up in a huge collection of exotic animals. And I remember when I was moving out when I was 18, to go to uni, my parents knew that I had a lot of snakes. They knew a couple of them were venomous, but they had no idea the extent of what I had in the house. And they were pretty surprised to find out not only did I have a king cobra, but it was nearly 5 meters long.
Oh my God.
I mean, I might as well be burying a hand grenade in the back of the yard at this point in time.
Yeah. That's crazy. That's so crazy.
So yeah, I worked, obsessively during my undergrad, which I did in the States. Just put myself under enormous pressure because I had to get near perfect grades to get a scholarship to do my PhD in Australia, because the scholarships for international students there's so few of them, and there's so many people who want to come here that at that point in time, and not much has changed, it was like 300 people applying per scholarship that was available. So and obviously, ended up getting one, but like I said, I put myself under, enormous pressure. I still, I had PTSD from that. I would wake up, even now, I still have dreams of, thinking that, oh my God, I didn't study for an exam, I'm toast. So it's, emotional damage. It's truly the gift that just keeps on giving.
That's funny. That's crazy.
So I did my PhD in Australia, obviously stayed here. And, because Australia truly is the lucky country, where it's the only country out there, or continent even, that has more venomous species of snake than non-venomous, where about 70% of the snake species here are venomous. So if you're into venomous snakes and other kinds of venomous animals, this is clearly the place to be.
Well, real quickly, so if you're, a lot of people listening say, well, why would you want to study it? Is it had to do with the medical part, or just a little bit of everything? What's your attraction to the venomous animals or snakes?
I mean, first off, I just have this, childlike wonderment for these animals that I find just, so intrinsically amazing. But also from a research side of things, it's a very dynamic area of research, because with the same data set of comparing a bunch of snakes that are related or distant from each other, or even regional populations of one particular snake, that one data set can have a myriad of outcomes, where not only will it contribute to the body of knowledge regarding, the evolutionary philosophy, the theoretical outcome of, how do animals diversify. Like, for example, Australia was venomous snake free up till only about 30 million years ago, when Australia was moving north. The continent of Australia was moving north and got close enough to Asia for it to be colonized by cobra-like snakes. So when these snakes encountered Australia, there was all these available niches. So when we're talking about evolution doesn't go on a steady step. It's not like a metronome that when you're playing the piano, ding 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 ding. No, it's more like ding 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 ding. So when these snakes came into Australia, there was this explosive diversification. This absolutely punctuated evolution, which is a theory that was first postulated by Stephen Gould, a U.S. biologist, a number of years ago. So there was this extremely rapid radiation, basically this race to redundancy. So in the first 5 million years, all of the snakes that we know of in Australia evolved. It was this explosion as they raced across the continent. And then once a niche is occupied, it's very hard to displace from that niche. So once an animal specializes for a particular microhabitat, they're pretty much going to own that microhabitat. So hence the race to redundancy.
Right.
So with that explosion of morphotypes, where the snakes no longer look like cobras, or all these dizzying arrays of size, shapes, and colors, the venom also radically changed at the same time, because they're now in a new continent encountering different prey, but also what you're feeding on is as important as where you're feeding on it. So prey escape potential is a very important aspect, as is how dangerous of a prey item. So, for example, taipans, the world's most dangerous snakes and the world's most toxic snakes, also feed on the world's most dangerous prey. So they're feeding on native Australian rats that would ordinarily be able to kill or or severely injure a snake, and also very dangerous small marsupials like bandicoots that again can severely injure or kill a snake. So taipans do this unique long distance striking, where they strike over half their body length, and they also do multiple strikes. So like when I used to have a big colony of taipans, I could throw a dead rat in, and not only would a snake be able to nail it in the air, but it would like hit it 2 or 3 times while it's still in the air.
Wow.
So that's why, like in human bites, they're so dangerous, is not only do they have this incredibly toxic venom, but they have insane amounts of it, and they bite repeatedly. Like there was one death to a boy at a garden party up around Gladstone a couple decades ago, where he got bit 12 times by a taipan in the space of seconds, just up and down both legs and around the groin area.
Jesus.
And obviously there's no coming back from a bite like that.
Wow.
So taipans are what I did my PhD on, because they're truly life at its most extreme. So people say, well, why does it have so much of this incredibly toxic venom? Because it's not just venom in snakes is not about killing the prey. It's about subjugating the prey. It's about just beating it to the ground and immobilizing it, because there's no functional difference between a prey item that's alive and aware and about everything that's going on, but it's completely paralyzed, or one that's unconscious, or one that's dead. They're all equally able to be swallowed. And even if they're swallowed alive but paralyzed, they're just going to suffocate in the stomach, or if they're unconscious, they're going to suffocate. So death is just sort of a byproduct. It's all about prey immobilization.
Yeah, right.
So in the case of the taipans, not only they're feeding on these incredibly dangerous prey items, so they need to absolutely nuke it to avoid prey retaliation, but also there's a high chance of prey escape. Like in the case of the inland taipan, they're feeding in the black soil regions with these deep cracks where the rat can go down quicker and deeper than the snake itself can pursue. So it's easy for the snake to lose their prey. So there's extreme selection pressure. So that's resulted in this extraordinary venom that when we talk about cobra-style snakes, we think of the classic paralysis, like of Cleopatra dying in this narcotic stupor after she clutched a cobra to her breast when her lover Mark Antony was dead and Octavian's armies were at her gate, and she was going to be taken back to Rome and paraded as a trophy in a cage. So she took the dignified way out. So, you die from that, paralytic effect. But with some of the Australian snakes, because they've encountered this new continent and they've had this extremely rapid radiation, and they're feeding on very dangerous prey, they could also escape. Instead, they've evolved venom that acts on our blood. And the way they've done that is it's really elegant. So when you think of venom glands, think of them as these really leaky kind of glands where they're just promiscuously expressing any protein found in the body, and just random, so they're just, like I said, leaky. So they just, anything that's in our DNA that's a protein that's encoded to be secreted, you're pretty much guaranteed to find that in low levels in some snake venom. And the way that any kind of adaptive evolution works is that through this random selection, if it confers a benefit, no matter how small, that this trait will become fixed and then amplified. So in this case, with this leaky expression, there is a blood clotting enzyme, our blood clotting enzyme called factor 10A, which is one of our major enzymes that we use to form a clot. So very early on in the Australian radiation, this came in as a trait, and then this was amplified in some of the lineages. And to a prey animal, it causes a massive overdose, basically, in clotting. And so it triggers a series of very large blood clots that result in catastrophic strokes. And as anyone who's ever seen someone have a stroke, you know how quickly they become immobilized. Half of their body is just paralyzed. Right. They can't walk. So in the case of a prey animal, they wouldn't be able to escape, or they wouldn't be able to fight back. So they're subjugated very, very quickly by these very powerful blood clotting enzymes. But what's fascinating is that in a human envenomation, we have a very different outcome, where because these blood clotting enzymes are diluted into a much larger blood volume, instead of forming a series of big blood clots, because the venom enzymes are spread out into 5 liters instead of 50 mil of blood, or 5 mil of blood in case of a small mammal, that it causes millions and millions and millions and millions of tiny blood clots that in and of themselves aren't going to do anything to us. We're not going to notice. You can have completely ruined blood and feel just fine until you start bleeding out of your eyes, because what it's doing is that it consumes all of our clotting factors. So it produces a consumptive coagulopathy, and then people die of internal bleeding, which is a really unfortunate way to go. It's not nowhere near as pleasant as what happened to Cleopatra. So it goes that sort of underscores of what I find so fascinating about the snakes is that with taipans, just with that one study that I did for my PhD, it had a myriad of outcomes spanning from evolutionary biology, of retracing how taipans evolved relative to other Australian snakes, and then other Australian snakes relative to Asian snakes, and tracing the emergence of these blood-acting toxins. So, really super cool from an evolutionary side of things. But that same data set has tangible, real-world outcomes that are the kind of data that's essential for clinicians to make evidence-based decisions in regards to clinical management strategies for an envenomed patient. So that one data set spans from theory to the real world, why should we care kind of outcome, all from that one pile of data. And that's been a persistent theme in the projects that we've been doing, is that all of these things are really cool from an evolutionary biology perspective, where snake venom is evolving faster than anything else out there. It evolves even faster than our immune system proteins. So it's, evolution absolutely cooking with gas, but cooking with gas while completely ripped on acid. The diversification is just extraordinary. But that means that, this evolutionary novelty, however, has real world immediate implications for human and veterinary medicine, because you can have, in a very short distance, you can have snakes that are genetically identical. There's no difference really, trivial differences, nothing, any kind of significance regards to taxonomy. It's all, for all intents and purposes, the same snake. That the genetics are, like I said, shallow little differences, but the venom differences can be spectacular. A perfect example of that is some work that we're doing with the Southern Pacific rattlesnake, which is found down around the Los Angeles area, that in just a 2-hour drive, we can end up with radically different venom types. So the ones on the desert floor, that do the classic rattlesnake action of anticoagulant effects on the blood. They just nuke our blood chemistry and cause us to bleed out of areas we don't want to bleed out of. But just, bog standard rattlesnake, nothing unique, everything you'd expect from a rattlesnake. But then if you keep driving, so, these are the first ones you'll bump into when you head east out of LA. And that, so, all right, fine, nothing novel there. But then you start climbing up into the San Jacinto Mountains. And as you get up to the top of it, these rocky, craggy areas where now there's a different type of prey escape picture. Because the first snakes you bumped into in the desert floor, a rattlesnake can just bite and release. That little mouse can stagger across the sand for as many meters as it wants, and the rattlesnake can easily follow its scent and retrieve it at its leisure.
Right.
But up in the mountains, the prey, if it's not knocked down very quickly, can disappear into the cracks of the boulders, and it's gone. It might as well go into a wormhole and pop out on the other side of the universe. It's gone from the perspective of that snake. So now, even if they're feeding on the same kind of animals, there's a selection pressure for a different venom type because of prey escape. But of course, they're going to bump into different prey that specialize for the high Sierra Mountains versus the desert floor. So you have different types of prey and a different prey escape potential. And that's resulted in snakes that are now powerfully neurotoxic. And the antivenom isn't working against them. So we have this evolutionary novelty, but we also have a clinical problem. But then now if you keep traveling and you cross over the big mountain ranges and you drop down, and you're now dropping down the dry side of the mountains, and you're heading out towards Arizona, but you're still still on the California side of those big mountain ranges, but the dry desert side of it, the venom changes again, and it's back to being blood acting, but in a completely different way. Now it's stimulating the blood to clot much like a taipan would, but using completely different toxins. And yet again, the antivenom fails. So you've got this one snake that is genetically indistinguishable, really. There's, like I said, trivial, shallow level differences, like 1% of 1% genetic difference. So we're talking trivial, means nothing. They are the same snake, but the venom has changed radically in these discrete populations.
Right.
And so that means, like I said, it's really cool from the evolutionary biology, but it means that if you map it out, that clinicians from these particular regions need to really focus in on, okay, well, what can happen clinically? Because treating a snake venom snake envenomation is the most complicated clinical emergency out there because any part of the body's physiology reachable by the bloodstream is fair game for a toxin.
Right.
So your nerves, your muscles, your cardiac system, and the blood itself. So, it's this absolutely catastrophic storm of events. So there's a lot of supportive care that needs to go in beyond just simple administration of the antivenom. So, and particularly in the case of some of these snakes where there is no effective antivenom for them. And that's another area that we're investigating is what else can be done. So we're looking at repurposed other medicines because the toxins that are causing these are very active little proteins, think of them as like little Pac-Man that are called enzymes, and they chew things up. Well, that means that if you have a drug that's an inhibitor of a particular type of enzyme and you flood the body with that, you can inhibit the venom.
Right.
So like the neurotoxic snakes up in the top of the moist part of the mountains on the western side of the ranges are causing the neurotoxicity through a type of enzyme called phospholipase A2. And there's an excellent drug out there called Veresplidib that was pioneered by my mate Matt Lewin up at the California Academy of Science and founded a company called Ofriex, where he had a very clever idea of using Veresplidib to inhibit this enzyme, and sure enough, it works. So that's in clinical trials now. It's cheap, it's readily available, and it's not temperature sensitive like antivenom is. So it means you can store it anywhere. It doesn't need to be kept in a fridge with continual power. So that means that it's the kind of drug that can reach people in impoverished areas of India or sub-Saharan Africa where there is only intermittent at best power supply. So in those areas, antivenom is stored away from where the bites are. They're stored in the rural, semi-rural urban centers, where they have continual power, which could be hours or days away from where the actual person who's envenomated is. So it has a lot of utility beyond just the medical side, but the socioeconomic aspects of it as well. So, and then we've looked at what's happening on the dry eastern side of the mountain where we have that procoagulant blood clotting venom phenotype.
Right.
And there's another type of drug that we repurposed called prinamastat and another one called maramastat that inhibit metalloproteases, which is what's causing the blood acting types there. So another enzyme class, but we have drugs that can be repurposed. So cheap, effective, and very, very useful. But like I said, this is all out of that one data set of tracing what's happening with this snake as you move through the different ecotones that it lives in, from the classic desert floor to the high Sierras, very lush, cool, highland areas like the San Jacinto Mountains, and then dropping over onto the dry desert-like side of the mountain on the eastern side as you transit down towards like the Mojave Desert. So it's a lot of fun work catching really cool snakes in beautiful areas of nature, but it has that we're geeks about evolution, but it has that immediacy that you can explain in 10 seconds to somebody in an elevator of why they should care, because this snake could kill you. We've shown there's no antivenom, but then we've shown that we could repurpose this commonly used other medication to save your life. So it has that public outreach that's kind of rare and wonderful in science, where anybody could understand why they should care, because people know that rattlesnakes do really bad things to you. It's not a state secret, and it's not like we're working on some obscure sea slug from a undersea mountain in Antarctica. People are going to care about the snakes because there's a chance of it affecting their own health and well-being or that of their family.
Well, I've got a question for you. So on the neurotoxin that causes the clotting, and you're talking about factor 10A, are they working with are they looking at the hemophilia ward with factor 8s and 9s and Epstein-Barr and stuff like that as well?
As far as using this as a treatment, not really, no.
Yeah, it's a different drug because it's expensive.
Yeah, and that's because they're replacing factor 8, which we need.
Yeah, right.
Need in our body. So no, this wouldn't help on any kind of hemophilia side of things, unfortunately. But there have been other blood-acting toxins that have made their way into the market. So, for example, a mate of mine Alejandro Alagon down at University of Mexico discovered a compound in the venom of the vampire bat that he ended up calling Draculin, which is the coolest name for a toxin ever. And this is in routine clinical use as the best stroke buster drug out there
Oh,
because vampire bats, of course, are feeding on blood. So when they bite into their victim, they have little small peptides that act as like anesthetics. So, the cow or the person doesn't feel the vampire bat chewing on them. And then they have other toxins that stop the blood from flowing. Stop the blood from clotting. They have other ones like we showed that increase the diameter of the little blood vessels on the surface of the skin to keep the blood going. But if the blood does clot, they need a way of breaking up that clot. So they have some anticoagulants that
right.
block the blood from clotting, but nothing is entirely perfect. So they have other ones that if a clot forms, they have these voracious enzymes that just chew apart that clot selectively like nothing we've ever seen out there in nature. And so this is an amazingly effective stroke busting drug where if they give this to a patient who's having a stroke and it flows to their body, as soon as it encounters that blood clot that's causing the stroke, it just chews it up.
There's a product called Activase back in my days when I was in the human side doing all that stuff too. So they called it a clockbuster, but it was so expensive. But in these, hospitals would keep a couple vials on stock, TPAs, I think was what they were called. But I'm wondering if that's replacing it now. That's totally cool.
Probably because recombinant protein expression used to be, cost an extraordinary amount of money.
Right.
And now that's become much more efficient. So it's, with economy of scale and better techniques. So yeah, what used to cost, 10,000 would cost, 1,000 or even just into the hundreds
Right.
nowadays to make.
Wow.
Another example of a venoms to drugs angle is if you know of anybody taking high blood pressure medication, odds are they're taking captopril or one of its derivatives. This captures about 90% of the market. And this was a drug that was developed back in 1976. So now we're coming on the 50-year anniversary of it. And it remains today, 50 years on, as a $10 billion a year market just for this drug. There's not a single other drug out there, that's that old that has that kind of market capture. That this drug is it's in the top 20 of all drugs out there. It's up there with like aspirin as far as its impact is on people. And that's derived from the venom of the South American lancehead vipers, that one of the ways that they knock their prey down very quickly is they render them unconscious by expanding the aorta, that big descending artery we have coming out of our heart. Basic fluid dynamics, if you keep the volume the same and you expand the diameter, if you keep volume and flow the same and you expand the diameter of a pipe, the pressure is going to drop, the simple fluid dynamics. So they expand these massive these vasodilatory compounds expand, all our arteries, and that causes the blood pressure to drop. And as we all know, from like standing out of a hot tub too quickly, if your blood pressure drops, you're going to hit the ground. So that's exactly what happens to their prey. They hit the ground, and then slower but lethal toxins have a chance to do their job without that prey being able to escape or fight back. So it was known that, in clinical cases, so you got again, that intersection between clinical medicine and drug development, they noticed that people who were bitten by these snakes had unusually low blood pressure that was stable for hours or even days. And so they isolated that compound from the venom, teased it apart, made a synthetic version of it that could be taken as a pill. So it was bioavailable through absorption in the stomach, which is the gold standard for a drug. You don't want it to be something you have to inject.
Right.
And so everything went right with this drug, and it's been, an absolute blockbuster. But to sort of illustrate the challenges of that, on the other end of the scale is a compound called ziconotide, which is an extraordinarily efficient painkiller from the venom of the Australian cone snails that you find like around the Great Barrier Reef. But the problem with this drug is that where it's acting, its site of action is inside of our central nervous system. And venom proteins can't cross into that. And they haven't been able to make a small molecule version of it that can cross over. So they're limited to using the native form, that can't cross, which means that the only way to deliver it into the spinal cord, so it can transit up into the central nervous system and affect the part of the brain that responds to this pain, is that they have to surgically implant a spinal pump, which is exactly as much fun as it sounds and as risky as it sounds.
Right.
So that means that for ziconotide, that it's limited to only the most extreme cases of pain that are intractable and are unresponsive to any other kind of painkiller, because certain pains only respond to certain painkillers. What we think of as pain
Right.
is a description, not a discrete state. There is no one pain. And I might, sort of sound like a sensei in a dojo at that point in time. There is no pain, and pain is an emotion. No, but it's a sense of pain is how we interpret something,
It's a description.
but the underlying mechanism can be radically different. So, for example, like if you have a sunburn, taking something like tramadol or morphine is actually going to be less effective than aspirin, because the type of pain receptors that we have on the surface of our skin are extraordinarily responsive to aspirin, far more so than any other painkiller. So the best painkiller for a really bad sunburn is just ordinary aspirin, because of that, that nuance. So there's a myriad of different ways that this can we can interpret pain, and that pain can be caused, and that we can treat it. So in the case of ziconotide, it's things like bone cancer that responds well to it. But like I said, it's only the most extreme cases. If they can make a synthetic version of these cone snail venom peptides that can be taken as a pill, that can then diffuse through the body and cross into the central nervous system, the market share would expand, by powers of 10, or 1,000-fold. You would have
Yeah.
a massive increase in the scalability of the market. But right now, the market share is tiny because of the physical limitations of how to administer this drug. And that's the biggest challenge with venoms to drugs research, is that the native form of these toxins typically is something that is very, very allergenic. It lights up our immune system like an absolute Christmas tree. That our immune system recognizes venom proteins as something we don't want to have in our body. This is not just foreign, but this is foreign and dangerous. So in the case of the Draculan, the stroke buster from the vampire bat, it can only be given one time because the person's very likely to react violently to it the next time. But one would hope that you only have one stroke event in your life. I mean, one would hope you have no stroke event.
Never. Yeah, exactly.
But if you're unfortunate to have one, you're hoping that's a one-off, and then from there on, you're on blood thinners, medications. You're proactively preventing a stroke rather than reactively having to treat it.
Right.
So in the case of Draculan, it's fine, because these should be black swan. A stroke should be a classic black swan event. Extremely rare, but absolutely catastrophic when it occurs.
Right.
So, but for something like pain, pain is a chronic condition. So using venom proteins in their native form can trigger, allergic responses. And that's been the biggest limitation of venom to drugs therapy, is making an artificial version that's small enough that it doesn't light up our immune system.
Right.
So in the case of the cone snail peptides, they're already naturally very small. They're only about 2,000 to 3,000 Daltons, which is the measure of molecular weight. So 2 to 3 kDa, tiny little things. Our immune system doesn't really recognize things less than about 4 or 5 kDa. So it's surfing under the detectability range. It's under the radar, so that's fine. But for larger compounds like Draculan, the immune system does recognize them. So in the case of Draculan, that's fine because it's a one-off use. But for other compounds, this could be a problem. So that's been the biggest limitation for other drugs to enter the market that are based off venoms. Lots of great activities, extremely successful in lab mice and such, but can't be used as therapeutics because they can't get a version of it that's small and not going to light up the immune system.
That leads us into the Komodo dragons, because I want to talk about them and talk about what you're doing now with the venom. And it's called the venom because different things you read out there when I was doing my homework I know you call it a venom, but some people call it some kind of protein or something like that. So is there some disagreements, or is it a venom that's in their mouth? But I want to talk about them, but I guess I'm asking anyways because there goes my mind bouncing someplace.
The Komodos are a fascinating example of how science changes. So when I did my undergraduate degree, I did a molecular biology major, but I also did a major in scientific philosophy, and then ended up picking up a minor in psychology to supplement, the honors degree that I was doing for the scientific philosophy in parallel to the honors degree in molecular bio. Because when I was looking at the scientific philosophy side of things, I was interested in how do scientific revolutions occur? How does new knowledge actually percolate? And that what is the role of the individual in this? Because everyone thinks of scientists as supposed to be this dispassionate, people sitting on clouds, staring at their big toe, and the data just, carries them wherever the data will go. No, scientists are people too. So they react like people. And there's this funny paradox that the less there is to support a long held position, the tighter people hold on to it. Which is why, like, if you're trying to convince somebody about climate change, the worst thing you can do is flood them with more data. That's actually going to have them just really dig in.
Right.
But so I was, very curious about, what was the mindset, and it's fascinating, that the more I dug into it, the more that you could see that people start acting psychologically less like a scientist and more like the follower of a belief system, a religion or whatever you want to call it. But
how about the politics in the U.S.? That's probably a good example.
Oh yeah. So they're not swayed by the data, which means that they're no longer acting scientifically, because the very definition of science is is all about the data,
right?
And it's supposed to be objective and dispassionate. But people are people, so they're no longer. If you're no longer following the data, you're following a belief system, and that's a religion. That's not science. And so that means that if you're following a belief system, that well, then how does this data actually end up becoming the new paradigm? And my final cynical conclusion at the end of my honors thesis was that scientific revolutions only properly get entrenched when the previous generation die out. And it's borne out very well by what's happening with the Komodo dragon stuff, where it's 20 years now since we published the first work showing that Komodo dragons are actually venomous and that they don't use bacteria as a weapon.
Right.
So there's two stories going on here. First is this whole idea of bacteria as a weapon came out in a book by a guy called Offenberg, who published a book in 1980 about the year he spent observing dragons in Komodo Island, Rincha, and the surrounding islands, in 78, 79. So in his book, early on, he notices, the occasional deer or water buffalo with an infection. That's the last you hear of it until towards the end of the book, where he presents this elegant but completely unsubstantiated theory that they're using bacteria as a weapon. And this has become a popular science keystone, that everybody knows about this, and it's something you've seen regurgitated in countless nature documentaries with absolutely zero data to support it. Now, the first thing you need to understand is that the water buffalo that they are feeding on that occasionally get infected are not native to these islands and are only actually found in a couple restricted valleys that have permanent water sources. But because the water buffaloes were left there by Dutch explorers who brought them along as food sources. Now, water buffaloes in mainland Southeast Asia, when they feel threatened, they bail into the large marshes that are around there, hence the name water buffalo. But in these areas, the only water sources available to them are these rocky, craggy holes that are stagnant. They're like maybe 2 or 3 times the size of your average backyard pool with no water flow. And they're full of water buffalo crap. And you can smell them hundreds of meters away. And I remember the first time that we did field work there, I was like, I better not go into that water, because I had a fresh cut on my leg from a small boating incident that we had. And then a little light bulb went off, like, no, it can't be that simple all this time.
Oh,
But it is, because Komodo dragons aren't from Indonesia. Komodo dragons evolved in Australia. There's nothing special about Komodo dragons in that they're just a very big monitor lizard. They're not the biggest to have lived. There's two extinct species that they lived alongside of, one that was about 5 meters and the other one that was about 7 meters. And Komodos at about 3 meters are the last of, the last living of the really big ones. We still have a lot of lace monitors here in Australia that are about 2 meters. So Komodos radiated out of Australia, subsequently went extinct in Australia when the megafauna declined that they were feeding on. So they would feed on like young diprotodon and things like that. So, but they persisted in some of these small Indonesian islands, the last refuge of Komodos. So they're not native from there. They evolved as ambush feeders of pretty much anything they'd go after. So they've experienced a number of different fauna, preyscapes. So with the buffalo, they'll have a go at it, and there's not a single event where they've killed the buffalo outright. Instead, the buffalo bails, and that's the last that Komodo ever sees of it. The buffalo then goes and stands in its own, warm feces that are cooking in the tropical sun, and occasionally they get a really nasty infection from that. And that's it. That's so the occasional water buffalo does get infected, but it has nothing to do with the Komodos. So we sampled the mouths of Komodos, including captive-born ones like that we sampled like out of the LA Zoo as they were hatching. The LA Zoo was so cool about this. So it was Hawaii and a few of the other zoos letting us get swabs from their animals. But what was fascinating is when we were doing that study of looking at the bacteria in the mouth, some zoos not only refused to participate, but they rang other zoos and told them not to participate, that we were
why?
crackpots. Well, we had already been publishing on the venom, and we're already, saying that Komodos are venomous and that there's nothing to do with bacteria in that. So we were threatening this enchanted fairy tale. And so it was bizarre that, some of the zoos, like I said, took it upon themselves to ring other zoos. I won't name names, but then when we published the bacteria results, we had a year-long battle with one intransient reviewer. And then the journal sat on it for another year until we threatened to take it to another journal to pull the paper. So it was, people were acting like religious adherents, even though there's no economic stake in Komodos
I know, it's wild.
not or using bacteria, unlike climate change, where it's very understandable that people feel threatened by the incontrovertible data because there's massive economics at work here.
Right.
But in the case of the Komodo, it was fascinating because there was no economic interest that was threatened. But what the irony is that in Offenberg's book himself, he, without knowing it, actually has in there the first evidence of venom, where they did these horrible experiments where they did things like they tied goats to trees, let the Komodo dragons tear into them, and then chase the Komodos off, and then just sat there and sat in the shade and watched what happened to these poor goats, and described that even like with their intestines hanging halfway out, the goats were unusually quiet, as if they were sedated.
Yeah.
They seemed very dizzy. They rapidly went into shock. They bled much longer and more profusely. They just sat there and watched them bleed to death. They bled longer and more profusely than you would expect from the mechanical damage alone. So all things that we've subsequently shown in the Komodo dragon venom is that they've got neurotoxins, they have toxins that drop the blood pressure, and they have toxins that block blood clotting.
Right.
And if you look at a picture of a Komodo dragon, or any other monitor lizard for that matter, if you look at the lower jaw, you can see this bulge running the length of the lower jaw. That's this large hollow gland that stores liquid. And this liquid contains all of the same kind of toxins as what's in the Gila monster, the iconic venomous lizard from Arizona. So same toxins, same gland, same morphology, yet people won't call it the same term, venom. We've had this ongoing battle with some people who refuse to call it venom. And it's fascinating, even though we have field observations, as do other people, of showing that when Komodo dragons bite a natural size prey animal, so in Australia, they evolved to feed on animals around 30 to 40 kilo. So when they go after a pig or a deer on the islands of Rincha or Komodo, they're going after animals that are within their natural prey range. Water buffalo at 1,000 kilo is clearly outside that.
Right.
But what's fascinating is you can see sort of a two-step aspect of prey death. Some of the prey are killed outright because the venom is there in a supportive role. The teeth themselves are already formidable weapons. They have these recurved teeth that are serrated on both the forward and back edge. They've actually got iron incorporated in it, to help them be even stronger. And so, like at one of our field sites, for example, to show how catastrophic the wounds are, a young local boy was killed when he went to use the toilet in the long grass and squatted down, and a big Komodo nailed him, sliced his femoral artery. First blood spurt went about 2 meters, and he bled out within seconds. And then the Komodo grabbed him mid-body and swung him into a tree, crushing his skull. So that shows from a mechanical perspective how efficient of killers they are. But so in our observations and that of other people, pig or deer, 60 or 70% of them are killed outright. But then enter the venom. The venom causes about another 20 to 25% of the prey to bleed out through longer and more persistent bleeding and greater volumes than you'd expect from the mechanical damage alone, just like Offenberg's own descriptions, that they would, over the next 3 or 4 hours, after being, they're being bit repeatedly by the Komodo, and they just keep bleeding and bleeding. They're, anesthetized. They're, staggering around so that prey escape potential is greatly lessened. They can't fight back. In the case of like a pig, which are quite formidable prey. So the venom itself gets them another 20 to 25% of their success rate. So this is putting them into like 90 to 95% predatory success rate, elevating them from that 60 to 70%. This is elevating them from predator to super predator. This makes them one of the most efficient predators out there, eclipsing a great white or an African lion. This makes them extraordinarily efficient in taking down prey. So I think that's one of the fundamental misunderstandings, is that we're not saying that venom is the only game in town when it comes to a Komodo, unlike something like a cobra, where their prey capture is entirely built around venom, but that the venom is there in a supportive role, but in a very, very, the best, the winner for the best supporting, role in a venom Oscar goes to, the Komodo dragon venom, where, supporting those, teeth is an extremely efficient, way of doing it. So, like I said, it's been the very public battles we've had with some people about this, and it just absolutely refuse to countenance the idea of Komodos having true venoms, even though they will quite happily accept a Gila monster being venomous. And here we have the exact same glands producing the exact same proteins that have a toxic effect and the exact same pathophysiological mechanisms of action. So, if it walks like a duck and quacks, it's a duck, so, the same term should be applied, but they refuse to. Now, part of it may be, that, like I said, people are responding as individuals. And I'm not the most diplomatic person in the world, and I'm certainly not the most humble person in the world.
You have your own. You're not opinionated at all, are you?
From a PR perspective, I haven't done myself any favors with, the sort of some of the very grandiose statements that I've made. Not to mention that, I've been, popping up on a lot of nature documentaries. Attenborough's commented about my work. I've been on BBC a number of times. Countless specials, on about Komodo dragons featuring it. So you got, my, handsome little mug popping up all over the place. So, like I said, I haven't done myself any favors in that side of things, but hey, I don't care.
Well, I know. I know you. I know what I know, and I know what I know. If you don't like it, screw you. I mean, at the end
Well,
of the
that's
day,
pretty
but
much been my attitude, And like I said, you're supposed to be more diplomatic, like the old Carnegie book of how to win friends and influence people. It's a checklist of everything I haven't done, basically.
well, you know what? Sometimes you're so busy doing things, you don't have the time to waste it kissing everybody's butt.
Well, yeah, I mean, I know, I do understand that I, have rubbed people the wrong way, and I'm certainly better at it now, but 20 years ago, hey, come on, this was my big thing. I worked so hard and so long on this, that I wanted to enjoy the spoils and I wanted to celebrate a bit,
Yeah.
and that doesn't that doesn't go down well. Jealousy is a very powerful professional force, as happens in many fields. So there is the scientific philosophy aspect of the paradox of people holding on tightly to something. As I discussed with my honors thesis, and then we have through to jealousy of me making a lot of money on a lot of nature documentaries and having a lot of fun celebrating this work. So that of course is a force multiplier.
Yeah.
But nevertheless, you still can't escape the fact that venom, it's a venom.
It is what it is. And you prove it.
For real, 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 for real.
And we'll be right back. We are supported by Prof, providing stem cell therapy for pets.
As a pet lover, did you know your pet can benefit from the incredible healing power of stem cell therapy? Prep Therapy offers a groundbreaking solution taken right from your pet's own blood. Say goodbye to joint pain, arthritis, kidney and liver conditions, and more. They'll experience faster recovery, increased vitality, and extended quality of life without the need for surgery or harmful drugs. Put the wag back in their tail and discover Prep Therapy today at prepvet.com. Save 10% with promo code FurRealPodcast, covered by most pet insurance.
It seems to me aside from that, how efficient they are. One is, I read that, first of all, and again, when I read things and do my homework, doesn't necessarily mean you're right because they're out there. I could have read something that wasn't venom, right? So I read that when I saw some videos. It's pretty brutal. I would not want to run into one of those things in the wild. But if they eat like a goat, they'll swallow it down in a few bites. But the body actually gets rid of all the bones and teeth. It fills it out through a mucus thing or something.
Well, they're very powerful enzymes in their gut. So when they swallow, some of the bones get digested, but they'll literally crap out like an intact femur. And we've seen that with other monitor lizards too. Like I remember when we caught a huge lace monitor here in Australia, which is the closest living relative of a Komodo, and it was pushing 2 meters. And when we got it home, within the first few days, it took a massive dump, and there was a kangaroo shin bone.
Wow.
That came out with that dump. It was extraordinary. So, same thing with the Komodo, that whatever they don't digest is just going to pass through.
Yeah. And they're able to do that. And then I read, because they're eating these big things from a deer or whatever, that they have a really slow digestive system and they can go with like 12 meals a year on the low end or something like that. Is that true?
Well, first you've got to keep in mind that they're a reptile.
Right.
So that means that they're not generating their own heat.
Okay.
Like an extraordinary amount of the energy that we intake, it goes just to producing our heat.
Oh.
Like I would say, nearly half of the energetic income that we have is just for heat production. That's why, like, if you live in a climate that gets really cold in the winter, you're hitting the carbs, you're getting your potatoes in, big time during the winter. You just have a craving of it because you need fuel for the furnace to keep yourself warm.
Right.
Versus, you hit the tropics and you're just going to be going after some, fruits. You're just naturally going to be eating less carbs. So with reptiles, their energy requirements are already much lower.
Okay.
And that with a case of like a Komodo, that they're the only lizards that actually dismember their prey. So when they eat like a 40, 50 kilo deer, they're going to be tearing it off in chunks, with these extremely sharp serrated teeth. So that means that they can sit there and they can take into like up to 80% of their body weight. They're almost doubling their body weight in food. And they've just got this huge belly full of food now. And they're just going to lay in the sun and burp for a while. And that they then will store all that energy, since they're not burning it off, producing their own heat, they'll store it as internal fat. So they have reserves.
Right.
And that's why, and they can also then survive loss of condition that would kill a mammal. Like at the end of the dry season, where they haven't eaten for 3 or 4 months because there's no food around, that their skin and bones, you can actually count the vertebra on their back. You can see you can just see their bones. You can see their scapula. You can see their shoulder bones. You can count the ribs. That a mammal in that condition would be picked apart by vultures because it's dead. At that point in time, these reptiles, because they're not producing their own heat, they can take their body right to the edge of starvation where we would quickly fall off that cliff because, we're our energy requirements. But, they just right to the edge, and then, they get a couple good meals, and then they just boom, bounce right back condition wise. It's incredible how quickly they bounce back. So it's, not so much they have a slow digestive system, but rather they have a slow metabolism.
Okay.
They need to digest the food in a fairly short order so it doesn't rot in their stomach. So that's why they're dark colored, so that they absorb the radiant energy of the sun very efficiently, and they heat up, and that their internal body temperature will get to the same internal body temperature of a mammal, but using the energy of the sun. And then they can start quickly digesting all of that food and then storing that energy as reserves.
What is that they have that? I know there's other reptiles that have it. Is it parietal eye that's on the top of their head that distinguishes color or something?
Yeah, so it's the third eye, and it's very common in lizards. And for most lizards, it's just this little disc.
Right.
And all it does is it allows them to distinguish shadow and light. So that way they can distinguish, like, if a predator is coming up behind them.
Okay.
Because, their eyes are typically focused forward or a little bit to the side, depending on what, the shape of the head is and what their predatory ecology is. But most of them can't, do things like, the trippy eyes of a chameleon that can move independently in all these different directions. So it's a very ancient trait within lizards, and it's at its most highly developed in the most ancient split off the lizards, which is actually a type of beaked dinosaur called the tuatara that you have in New Zealand. And it's got the most advanced of these third eyes, but it's still retained in a lot of lizard lineages, including in, different monitor lizards.
So it's kind of like a skylight.
Effectively, yeah, that it allows you to just distinguish, a radical change from, light to shadow, which indicates that something's coming up behind you. And that's enough information to, avoid being dinner sometimes.
Well, I got to pronounce the word someday. Anyway, so two other things, and then I don't want to take all your time. So what's the deal? So when they eat all this stuff, they have a flexible skull. What does that mean? I mean, I know what the word means, but what does that actually mean?
With a lot of a lot of lizards and also snakes, and snakes just are a highly tuned form of lizard. What we call a snake is just one of 25 lineages of lizards that have lost their legs. It's just the most derived form.
Right.
But they have highly kinetic skulls that, unlike mammals where, we have very rigid skulls, and that's because we have very strong bite forces. If we had flexible skulls and a strong bite force, your skull would split apart.
Okay.
Versus lizards don't have that level of bite force, but they have very flexible skulls that allow them to eat very large objects. So we're crushing and tearing objects. Lizards eat typically swallowing things whole, and so they need, when they're biting down hard to kill a prey, they need their skull to be able to deform a bit to accommodate, the kinetics of, biting without the skull itself splitting apart. So if a Komodo dragon had the same bite force as like a wolf, his skull would explode.
Okay. Well, that makes a lot of sense to me. And I want to get an article I read there, but can you talk just for the people that are listening that I've done it and I've read it, but can you talk about how big they are and how fast they are? And then I want to get into one of the things I read that you had talked about after that. How big are they?
Komodos, are reputed to reach up around 3 to 3.5 meters, typically a little bit smaller than that, but still big. Body weight, up to around 100 kilo. But to put this in perspective, with something like Megalania, the extinct, 7-meter giant, that if we go from 3.5 meters to 7 meters, we've doubled the length, but we've quadrupled or the other aspects, and then we end up with an 8-fold increase if we go. So double the length, double the width, double the height. So that means scaling up, that Megalania would be conservatively 8 times the weight. So it's estimated that Megalania was 800 to 1,000 kilo versus the 100 to 120 kilo of a Komodo. But Komodos, they're still big, very formidable lizards.
They're huge.
They're quite fast. Where the monitor lizards are unique among lizards in that they've got something called a hyaloid bone. So when you look at a monitor lizard and it puffs its throat out, that characteristic, they can make their throat just puff out and hold it. They have a bone that they do that with. But what this does is it allows them to force air into their lungs much like the bellows that you would use on a fire.
Right.
So when they're unlike other lizards, they can force a lot of air in beyond just simple breathing by moving that hyaloid bone in and out. So that gives them an aerobic capacity exceeding that of other lizards. Like we've chased monitor lizards across the desert here, and we've had to run after them for like 300-400 meters before we finally get them. And sometimes we don't get them; they just keep on going. They outrun us like you wouldn't believe, and it's hilarious. To get burnt by a big lizard in the middle of the open desert where there's nowhere for it to go. There's no hole, but it just outruns us. But something like an iguana wouldn't be able to do because they don't have that same aerobic capacity. So they can get up to top end speed quite quickly, and then they can hold that speed more so than you'd expect from a typical reptilian physiology. So they're extremely formidable, but they're also so cluey. They're like dog level intelligence. Like if you look at the difference between a lace monitor versus a Komodo and the jump in intelligence with this increase in size and longevity, where lace monitors live 40, 50 years, Komodos live estimated 80 to 100 years. So then if we extrapolate from that, it's estimated that Megalania, the 7-meter giant relative of the Komodo, was estimated to live over 200 years. And so therefore, if we look at the intelligence of a Komodo and then we, relative to the intelligence of the smaller lace monitor, and then we stepwise increase that to Megalania, Megalania would have been extremely smart animals. Because like Komodos are smart enough that they play. Some zoos have had habitat enrichment where Komodos will actually play with a bull, or Komodos have been shown to take a dislike to a particular keeper, and that keeper can't work with them anymore. And like we have this one where on the BBC Natural World, I think it was Secrets of the Dragon's Venom or something like that was the title of it. But you just do BBC Natural World Komodo, you'll find it. And on this one, there was a Komodo that I was by. It was a big Komodo up around 3 meters. And it was just chilling in the sun. And so I came and I sat nearby it. And we actually played peekaboo because
Bryan, that's exactly what I was going to bring up. Is this thing? This is exactly what I was going to bring up.
So it would close its eyes and pretend like it was asleep, and then I would close. But you could actually see it squinting. So it's smarter than your average 2-year-old who, when they close their eyes, they think they disappear. But so that means that they have a level of sentience, aware of themselves in fourth dimensional space. So not just in place, but in time. So it would open its eyes just a little bit, see if I was looking at it. And then if my eyes are still open, it would close its eyes again, but it would squint. But if my eyes were closed, or I was squinting too, it would open up its eyes all the way. And then you could see it thinking about, should I have a go at this guy? Then if I'd open my eyes again, it would close its again. And we did this for like 15, 20 minutes. And it was the most remarkable interaction that I have ever had with any animal. Where I've scuba dived with whales, I've been around big primates, but nothing could top the interaction that I had with this wild Komodo dragon and this blink, 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 blink back and forth. They're just thinking about it now, it still just blows my mind.
That literally is where I was going with that thing, that article. I'm reading that thing. That is way cool. I want to ask you one thing. It's not Komodo because I don't know anything about it. I did an episode with Jennifer Mathers, who's an octopus expert, but talk to me just really shortly on the Antarctic octopus. I didn't know that octopus had a venom. I know they got the black ink, but I didn't know there was a venom. Just real quickly, can you just touch on that?
Yeah. So most people have heard of, certainly in Australia, the blue-ringed octopus, and they think that that's the only venomous octopus. No, it's just the most venomous octopuses. But all octopuses the world over are actually venomous. Like if you go scuba diving, you'll come across clam or other bivalve shells that have a characteristic little hole in the side where the octopuses come by, use their radular tooth to drill through the side of it, and then the clam opens up. They don't just tickle them into opening up, they inject a venom. So, and aquarium keepers know this, people in Australia, the keepers here know that the Maori octopus, one of the big southern octopuses, will cause your arm to swell up to look like a Hulk arm. If you get bit by it, it's not lethal, but you're going to have massive local swelling. Other octopuses are known to cause, a bit of light neurotoxicity. So we got a grant to go down to Antarctica to collect venomous octopuses down there. And the entirety of our grant application, you could rewrite on a post-it using a child's crown, which is that, no one has ever looked at Antarctic venoms, the end. Of course, we spent about 20 pages explaining it a bit more in detail, but, our idea was that, Antarctica, there's a lot of that life under the water there. Like, you think of Antarctica as being a desert. Well, it's a white desert up above, but under the water, Antarctica has as much, if not more life than any other marine zone out there. It is extraordinary how much life is happening underwater there. So we spent 2 months at sea, zipping around Antarctica, and we ended up collecting, so we were dragging nets all the way down to 4K down, 4 kilometers down, where we were pulling things up that were so bizarre. The only reason I knew it was a life form was that it moved. That's about as far as I can tell you is that it's life. Other than that, I couldn't even tell you which kingdom it's in.
Wow.
So, like things that I thought were corals were actually some sort of, or some sort of cnidarian. So, we had all kinds of weird things popping up. So with that, we got 254 octopuses, including several new species. And we did the first and still the only investigations of Antarctic octopus venoms. What is life like, what is venomous life at the poles? And it was fascinating where some of the compounds were enzymes, these Pac-Man-like active things that chew things up. Well, enzymes are very sensitive to temperature. And so that's why, we have certain enzymes that are really useful at very high temperatures. Like when we do PCR, when we do, polymerase chain reactions and we look at, tests to amplify DNA, we use a type of enzyme from deep sea thermophilic life. It is from bacteria that live at deep sea hot vents, where they have enzymes that are really active at hot temperatures. So we run PCR at very hot temperatures so that no other enzyme is in there. Our DNA is safe and intact, and the only enzymes in there are the polymerases from this hot vent deep sea life that are active at 80 to 90 degrees. And that's, but if you run these same reactions at 20 degrees Celsius, so that's 80 to 90 degrees Celsius, so, pushing water boiling temperature.
Right.
But if you run that same reaction at 20, nothing's going to happen. So we know that enzymes have a sweet spot for activity. So we were curious, and we looked at the Antarctic venom enzymes, because some of the compounds were chewing up the flesh of their prey and helping disrupt the prey physiology that way, and also a bit of predigestion. So we showed that these enzymes are extraordinary, where they're at their sweet spot at 0 degrees to 2 degrees Celsius. But if we compare that with the same kind of venom enzyme from octopuses that we collected in the tropics, like from the Barrier Reef, that same enzyme class, same toxin class, that those enzymes had their sweet spot at around 25 degrees C, which of course fit with the water temperature that these octopuses were living in, because octopuses, like reptiles, don't generate their own heat. So they are their body temperature is whatever the ambient temperature is. So it was really, really cool, this venom on ice, as we called it, to show, that these venom enzymes, so we took the polar ones and we tested them at 25 degrees C, they just fell apart. And if we took the tropical octopus's venom enzymes and ran them at 0 degrees, they did nothing. They're just paralyzed by the cold.
Wow.
So, from the adaptive evolution perspective, it was really, really cool.
Right. That's so cool. Yeah, there's so much. God, I could talk. Like I said when we first talked, we could have talked for days, but I don't want to.
Oh, I could talk for days, and I have been known to.
I have too. Trust me. That's where we're in a bar drinking beer together. We'll never leave. So, is there anything that you would want to bring out there that we didn't cover? For the audience, just that would be that we left out, or anything you can think of for now. I'm sure we left out a gazillion things. But anything?
Well, I would say just public service announcement that when it comes to venomous snakes, don't be stupid. Where a mate of mine who's a clinician in Arizona has what she calls the 4T rule, where she actually plotted the 4Ts relative to snake bites, and particularly snake bites that were not legitimate. Where a legitimate one is you're gardening, you don't see the snake, you get bit. That's a legitimate bite. An illegitimate bite is the hold my beer scenario, and you start messing with the snake. So the 4Ts were the number of testosterone. The number of tattoos, level of testosterone, meaning males are more likely,
Yeah.
number of teeth missing, and the number of shots of tequila. Often they're heavily inebriated. So in illegitimate bites are typically to young males, usually a couple beers in. And then, perfect example of why men die sooner. It's a myth that women live longer. No, women just live out to their natural lifespan. Men typically don't live to their natural lifespan because we're stupid.
Right.
We are, our like the part of our brain that assesses risk actually doesn't develop to its fullest in the male brain until the early 30s when the testosterone levels start dropping. Our high testosterone levels suppress our risk assessment, which makes sense because, with most species, it's the male that does the dispersing. It's the males that do the risky breeding behavior. So you don't want them to be assessing risk because, the species will go extinct.
Right.
It's fine if 9 out of the 10 males end up as a hood ornament on the car of life. As long as one male gets through, it can impregnate multiple females. So, I certainly did many stupid things in my early 20s, but there's this, even in Australia where, people are very snake aware, most of the bites that I would say at least, half, if not more of the bites that are present at the hospital are illegitimate, where people have done the wrong thing.
Right.
Like if you see a snake in your garage, if you have enough time to walk away, get a shovel, and come back, clearly you are in no immediate danger. So if you try to kill that snake, rather than ringing your local Parks and Wildlife, and they'll send out a licensed snake catcher for a nominal fee who will safely remove it. If you try to kill that snake and instead you injure it, the snake is now viewing you as a predator, a threat.
Right.
So it's, of course, going to retaliate. And when you inevitably get bit, you do not have the divine right to throw yourself to your knees, raise your arms to the heavens, and plaintively cry out, "Why me?" Because you were a tool. That's why
Exactly.
you did the wrong thing.
Oh boy, we've all done that at some point in our life, I'm sure. Now, I sent you a thing about telling a joke. I don't know if you read that thing or not. Do you? By the way, the jokes I have are you're gonna cringe more than you've ever cringed. Do you have one? I've got one, but if you have one, I'm happy for you to tell one.
Oh, go for it.
Okay, so by the way, all the audiences out there, you guys know, if you've listened to me enough to know that they're the worst jokes than ever. And I'm always asking, and as you know, I've had people on, if you want to tell a joke, your kids want to tell a joke, nieces, nephews, grandchildren, if you send me an email at mkyle@forrealpodcast.com, I promise you I get back to everyone. Okay, so here's I'm apologizing before you get it. So, why is it easy to tell how much a Komodo dragon weighs?
I don't know.
They come with their own scales.
I love it.
Okay.
A big proponent of dad jokes. I think that they are an underappreciated art form.
Absolutely.
So I will take that joke and I will move that joke straight into the database.
Yeah, it's actually it.
I have a 4-year-old daughter, so I'm licensed to tell dad jokes now, and she loves my dad jokes. And my wife keeps telling me, enjoy it while you can. Soon she's going to start eye rolling. And she's already started eye rolling now that she's 4.5, and she keeps reminding me.
My kids have been eyeballing for years, and I'll give you a bunch when we get off of this thing too. It's pretty funny. But anyways, first off, Bryan, thanks so much for being on the show. This is fascinating. I love a science question and solid new science knowledge. So seriously, thanks so much for being on.
My pleasure.
And then for everybody else that's listening, as I always say, keep following, pass the word out, keep listening. The more you do that, the better opportunity I have to have good guests like Bryan. But if you got ideas for the show too, send me an email. I really would appreciate it. But lastly, from the most important thing, from the bottom of my heart, thanks so much for listening. For real.
That concludes this episode of For Real with your host, Mark Kyle. For previous and future episodes of For Real, listen via all major podcast streaming sites.